Here are solutions to homework set number 11 for ECE 111, Intro to ECE. This homework set looks at inductors, specifically the VI characteristics of an inductor, and then the differential equations that result in RLC circuits. Specifically, you wind up with coupled second-order differential equations, which leads to the wave equation. Now the first problem is, suppose I have the current through an inductor looking like so. If that's the current, what's the voltage? Well, the VI characteristics for an inductor is the voltage is L times the derivative of the current. So if I take this waveform and find the derivative, I get the voltage, since L is 1. The derivative is the slope. Slope is changed in the current in time. So initially the change of the current is 0 in 1 second, so the voltage is 0. Between 1 and 2, the current changes by 2 amps in 1 second, so the voltage becomes 2. The slope goes back to 0. Then again it goes up by 2 in 1 second, becomes plus 2. Between 4 and 5, it's again 0. Between 5 and 7, it changes by minus 9 amps in 2 seconds. 9 over 2 is 4.5, so it drops down by minus 4.5, goes back to 0, becomes plus 5. Then it goes back to 0. So this is V of t. So capacitors, what we covered last week, are integrators. Inductors are differentiators. In problem 2, this looks at find the differential equations that describe this circuit. Now I know right away this is going to be an 8th order differential equation because I have 4 inductors, 4 capacitors. That's 8 ways to store energy. That gives you 8 coupled differential equations. Now the way to write the differential equations, there's a couple ways to do it. What works pretty well for this homework set is as follows. The basic equation for an inductor is the voltage is L times the derivative of the current. So for the first one, you use the dot notation. Dot means derivative. So for the first inductor right here, looking at node 1, I get V0 minus V1, as the voltage across it, is L times I1 dot. The second inductor over here, the voltage across it is V2 minus V1, is L times I2 dot. For the capacitor, IC, for capacitors, V1, or try that again, the current to capacitors, IC, is C dB dt. That's C V1 dot. So those are the basic equation. That's the equations for inductors, equation for capacitors. That gives you coupled first order differential equations. Now for this problem, there's kind of a way to simplify it. Not really obvious, but here's kind of how it works. Conservation of current, IC, is I1 plus I2 plus I3. If I take the derivative, again, I don't know I1, but I do know I1 dot. I also know I2 dot. So take the derivative. There's the second derivative, first derivative, first derivative, first derivative. I can now substitute. CB1, second derivative, is substitute. I1 dot is V0 minus V1 over L. I2 dot is V2 minus V1 over L. And I3 is minus 1 over R times V1. That's I3. I3 dot will be V1 dot. So here's kind of what you get. Get the equations, the derivatives. Take the derivative and substitute. Gives you these equations. Now solve for the second derivative of V1. When I divide by C, I get a plus 1 over LC times V0. Minus 1 over L minus 1 over L gives you minus 2 over LC times V1 plus 1 over LC times V2, and minus 1 over RC times V1 dot. Plugging in numbers, here's the differential equation that describes node 1. Now by symmetry, nodes 2 and 3 will be the same. The oddball is node number 4. At node number 4, there is no node number 5, so you miss a term that gives you this equation, or that would be for double prime. So these are the differential equations that describe the circuit. To solve, as soon as you take, or when you take Calculus 4, I think you'll solve this type of differential equation. We're not in Calc 4 yet. Here's the beauty of Matlab. If I can get you the differential equations, I can solve. Now the solution is a little bit different than last week. Last week we looked at coupled first-order differential equations. That'd be like an RC circuit or heat equation. If I had the same equations giving you the first derivative, that'd give you the heat equation. Here's how the heat equation behaves. And nothing too wild. It warms up, settles out. That's the heat equation. Let's make that coupled second-order differential equations. So there's the second derivative. To get the voltage, I take the second derivative, integrate once, I get the first derivative. Integrate again, I get the voltage. Same as before, I know the initial voltages, I calculate the second derivative, integrate twice, and then plot it. Here's what coupled second-order differential equations look like. Again, remember the heat equation, you just warmed up and then stopped. Here's the wave equation. Behaves very, very different. And you see the wave equation over and over again. It describes ocean waves, of course, buildings, transmission lines swaying in the breeze, bridges oscillating up and down in windstorms, transmission lines bouncing in the breeze. Also describes circuits. If you have a circuit, wires are inductors. There's energy in the magnetic field as you apply current. There's capacitance and resistance. So if I have a long wire at really high frequencies, here's how wires behave. This is called the wave equation. So that is the answer to problem number 3. Solve when the input is 10 volts. And here we solve using numerical methods. The voltages just bounce all over the place. A lot different than the heat equation. Problem 4 says, okay, let's expand this to 30 nodes. Now there's a couple ways to do that. What you could do is take the old answer right here and copy it 30 times. Perfectly valid. This is where arrays are nice and for loops are nice. If I treat the variables instead of being just individual ones, make that a 30 by 1 vector. So here's my voltage. It's got 30 elements in it. The derivative of voltage, 30 elements. The second derivative. The differential equation is then for each node. The second derivative is 33.3 times the previous voltage minus 66 times the current voltage plus 33 times the next voltage minus 0.0227 times the derivative of voltage I. That works for nodes 2 through 29. And here's where for loops are nice. I don't have to write that equation 30 times. Just throw it in a for loop and increase the index. The oddballs are nodes 1 and 30. Matlab hates index 0, so I kind of have to type this in by hand. V0 is the voltage at the left. I can't call it V of 0 because Matlab hates index 0. And the other oddball is the last node. Its equation is a little bit different. Instead of 66, it's 33. The reason being is there is no node 31. It just stops. Now instead of integrating 30 times like I did here, since this is a vector, I can just say do all 30 integrations at once. The new velocity is the old velocity plus acceleration times time, and that does 30 calculations all at once. Once I know the velocity, integrate to get position. Plot position and repeat for 20 seconds. Now this guy right here just makes the graph kind of nice. Instead, let's just make V0 equals 1. That'd be a step input. That doesn't plot quite as nice. Here's how a step response looks like. So the first voltage goes to 1. This is why it's called the wave equation. Kind of see that one propagating down the line? This doesn't plot quite as well. What works a little bit better is a rope snap. That's what this does. It gives you half a sine squared, or half a sine wave for the first 2 seconds, then goes to sleep. So if I plot that, let's go over to Matlab, Control C, stop this program. And run this one. Here's my sine squared. That's my wrist snap. Launches a wave. And now you can see why it's called the wave equation. I launched a wave, and the wave travels down the circuit, hits the right endpoint, and this is a reflection. It then reflects back left, travels back down, hits the left endpoint. The left endpoint is fixed. At fixed endpoints, I get a minus reflection. There's the minus reflection. It then travels to the right. The right endpoint is free. At free endpoints, I get a plus reflection. So as a negative wave coming in, I'll get a negative wave reflected back. That's the wave equation. Okay, the next problem's on the homework. Let's look at the right endpoint. I'm just going to run it for 10 seconds. It's long enough that I launch a wave, watch it hit the right endpoint, and you get a reflection. So there I launched a wave, travels down the line, hits the right endpoint. Here's a free endpoint. The voltage isn't being constrained, it just jumps up to 2. If I leave the right endpoint with a high impedance, high resistance, I get a plus reflection. What happened is over here in the circuit, go back to the circuit, the right endpoint right here, R is really large, 220 ohms. If I make it infinity, a really large resistance, so I'm not drawing any current, what happens in the simulation is this guy right here becomes 0. So to make that 0, a really, really big resistance, I get a plus reflection. So trying it, here is that number right there is 0. The resistance on the right side is infinity. What you see is the right endpoint over here moves freely. There's nothing stopping the voltage from going up and down. If it moves freely, I get a plus reflection. So that's what happens when R30 is really, really big. What happens if it's really, really small? This is 1 over RC. If 1 over RC is 100, let's see what happens. So if we look at the right endpoint will barely move. That's because R is very small. I can't have a large voltage with a small resistance. Right endpoint barely moves. And what happens is you get a minus reflection. Now both of these are bad. The reason they're bad is if I have, say, a bunch of signals coming in, like this case, a bunch of sine waves coming in, and let's run it for 19 seconds. Speed it up a little bit. I've got a sine wave coming in. That causes a wave to propagate down. I get reflections. Those reflections cause standing waves. Those standing waves are high voltages. They can burn out components. If this is a bridge, it causes the bridge to collapse. If it's building in an earthquake, causes the building to fall down. Negative reflections are bad. They cause reflections. Really stiff is bad. Cause reflections. How do I get rid of reflections? Well, that's kind of what we're doing here. When you take electromagnetics, you'll be able to calculate it. In Matlab, I can find out by trial and error. So this number right here I'm playing with, 100 is too big, and 0 is too small. So let's try 30. And let's just run it for 9 seconds. I want to watch what happens when I launch a wave. How much reflection is there? So at 100, it was negative reflection. At 30, it's still negative reflection. Better, but still too big. Let's try 20. Launch a wave, goes down, hits. It's better. Still negative, so 20 is too big. Let's try 1. Now the endpoint moves more freely. There's more resistance at the end. 1 has a plus reflection, too small. Let's try 3. Better. I still have a plus reflection. Let's try 7. Get a reflection. Ooh, that was pretty good. Still slightly negative. So 7 is too big, negative reflection. Let's try 6. When you take electromagnetics, you'll be able to calculate what resistance I need to stick at the end to stop reflections. This is where Matlab is nice. If you haven't had electromagnetics, I can still find out what the answer is just by trial and error. Guess again. So it looks like at 6, I get no reflections. Where that's significant is, suppose I have a circuit. I am taking the left endpoint, making it go up and down, or this is a bridge with a wind exciting it, transmission line, anything described by a wave equation. If I terminate the end correctly, instead of getting reflections, I just take the energy when it hits the right side. All the energy gets absorbed. There's almost no reflection. What that does is that stops you from getting standing waves. So that is homework set number 11 for ECE 111, solving RLC circuits using Matlab, which leads to the wave equation.